So in the last video, we talked about how to simulate coin flips and rolling dice. Today, we're going to do a little bit more of that, and I'm actually going to take advantage of another feature that can rapidly produce a list of coin flips or rolling a die or any other kind of simulation that has a specific outcome. So just a repeated question here, when you flip a coin, the theoretical probability of getting heads is a half or 50%. Does that mean if you flip a coin 10 times, you will get heads? 5 times is then no different than yesterday. The answer to this question is still no. When you roll a standard six-sided die, the theoretical probability of rolling a 6 is 1/6 or 16.6 repeating percent. Does this mean that if you roll a die 6 times, you will get a 6 one time? Again, that is no. These two scenarios that we're talking about here are called binomial probabilities. Binomial in the sense that you can consider it a success or a failure of one of these two things happening. You could either get a 6 or not get a 6, or you could either flip heads or not get heads, which at least that one has actually two different outcomes. Some people struggle to wrap their head around the idea of rolling a die as two different outcomes. But again, if we focus our attention on the one outcome we're looking at, we can actually view it as a success, again, rolling a 6, or a failure, not rolling a 6. So we're going to take advantage of the random binomial feature on the calculator. So yesterday, I'll show you, I actually have it pulled up here. If I do a random integer 0, 1, 10, that shows each individual coin flip. And you could actually see that when I did this scenario here, I actually got 5 heads and 5 tails. But I could actually get a list for a single value. So if I go to probability random binomial, and then I want to say I want to do 10 coin flips. So I do 10 comma, and then I have to talk about what the probability of a coin flip is, or at least obtaining what we want, in this case tails or heads. That would be 0.5. And now each number I get when I hit enter is going to say you flipped a coin 10 times and got 5 heads. And then if I keep hitting enter, 7 heads this time when I flipped 10 coins. 4 heads, 6 heads, 6 heads. And again, I could even generate a list. And I could say, all right, if I want to do 10 comma 0.5, and I want to say, all right, right here, if I do this, I'm generating a list of 10 different numbers, but these numbers is actually saying I've flipped a coin 100 times. And the first value here is saying in the first 10, I got 3 heads, and then the second 10 from 11 to 20, I got 5 heads, then 21 to 30, 4 heads, so on and so forth. And so we're going to take advantage of that today. Again, if I wanted to do a coin flip, then I would just change this number. Instead of being 0.5, I think about the probability of rolling a 6 as 1/6. And now you can see, actually I'll just delete this, and I get, if I roll a die 10 times, I got 0 6s, then 3 6s, then 0 6s, 3 6s, 4, and so on. So we're going to take advantage of this to generate some data. First, we'll do it by hand on a table of values and making our own dot plot, but then we'll let the calculator take over. So if I wanted to simulate 10 coin flips 20 times, I could actually tell the calculator to do random binomial. So if I just cursor up, highlight that, hit enter. So we're going to do 10 coin flips. So 10 comma 0.5. And then if I put a 20 here, I'm going to get a list of 20 runs of 10 coin flips. And so I could actually just fill in my data here. I have 5, 5, 1, 4, 5, and so on and so forth. And so you guys could do this on your own. Again, you do not have to change the seating on the calculator if you've done this already, because you are not set to the factory defaults once you've done it once. The only time you have to worry about that is if you actually hit the reset button on the back of your calculator. But I'm going to let you fill in the data now. So here you can see I've actually also filled in the dot plot. This time for me, 5 was the most common outcome, and as it should be based on the theoretical probability. But again, we only did 20 runs of 10 coin flips. So we're going to now do the same thing with rolling a die. We're going to roll a die 6 times and repeat that process 20 times. So we have 6 rolls of a die, 20 runs of 6 rolls of a die. So I'm going to go ahead and do my random binomial feature here on the calculator. And if we're doing 6 rolls of a die, so we're going to do 6 there. The outcome of getting a 6 is 1/6. And again, we want to iterate this process 20 times. So I'm going to get a list of 20 numbers, lots of 0s, 2s, and 1s. And that kind of should be expected, right? It should be centered around 1-ish because of the way that the theoretical probability works. All right, so I'm going to go ahead and fill in that data in my table. So again, there's my data. It looks a little skewed, right? We would expect it to be centered around 1, but honestly, if I calculate the average of that might come out pretty close to 1. Obviously, it's going to be a little bit below it, but relatively close to it. And so we'll kind of explore that, especially when we run even more simulations, right? So we're going to, if you haven't guessed it by now, we're going to be taking advantage of the list and spreadsheet to simulate this even more rapidly. So when we did 20 runs, we were able to come up with our own hand-graphed dot plot, but now we want to do 100 runs of 100 coin flips. So I'm going to go ahead, maybe I'll even start a new document here. So I'm going to add a list and spreadsheet, and we're going to do coin flips first. So I'm going to do H for heads, and in this equals box here, I'm going to fill it with random data. So I'm going to go to data, random, binomial this time. So we're going to simulate 100 coin flips. And since it's 100 coin flips, we're going to do 100, 0.5. And I want to run that simulation 100 times. So that second 100 that I just put in there is going to tell the calculator to only fill in 100 data values in there. So if I hit enter, that quickly, we just simulated 100 coin flips 100 times, which actually is 10,000 coin flips that rapidly on your calculator. It's actually very impressive when you think about it. So again, we're going to focus on the dot plot of this. So I'm going to add a page by hitting Control Doc, and I'm going to add a data and statistics page. We labeled our column H. If you're not seeing an H there, it's probably because you forgot to label the column as such, right? We got to put an H up here in this box. And there you can see, again, is our dot plot. And as expected, if I did 100 coin flips, you would expect the values to come out to be pretty close to 50. And so we're going to answer a few questions here. So when flipping a coin 100 times, what is the probability of getting heads 50 times? So we're going to do this based on our theoretical probability. So if I count, I have 1, 2, 3, 4, 5, 6, 7, 8 dots. So we had 8, and I'm not going to bother counting all the dots because I know, based on the way I type this into the calculator, I have 100 dots. So I have 8 out of 100, or 0.08. What is the probability of getting heads 60 times? Well, if you pay attention to the scale here, that's 58. That would be 60 right there. Even when I hover over it, you can see that I got it. So that 2 out of 100, or 0.02. And then probability of at least 60 heads. Then I go to 60 or higher. We have those original 2 plus 2 more, right? 61 and 63 fit into that classification there. So we have 4 out of 100, 0.04. All right, so we've just simulated 10,000 coin flips right there. So I'm going to go ahead and see what we got on the next page. So this time we are going to simulate the rolling a die and getting 6s. So you can see here, I'm showing you how to type this in. So I'm going to go ahead, maybe I'll even start a new document again, right? Because we have nothing to do with the flipping coins in this one. So I'm not going to see any changes. Add lists and spreadsheets. This time I'm going to label it S for 6s. Go to menu, data, random, binomial. So we're going to simulate 30 rolls of a die. So 30, 1/6, 100. So we're going to have 100 dots on the dot plot again because of that 100 there. And so my number should range anywhere from 0 to 30. It'd be very unlikely to get 30 sixes. So we'll see this though when I go to add a page, add a data and statistics page, and I look at all the numbers of sixes that I got. So there was one time where I was only able to run 1 6 out of 30 rolls of the die. Then there was 10 sixes out of 30 rolls of the die. And actually, this is not a surprise to us that it's centered around 5, because 5/30ths is 1/6. So what is the probability of getting a 6 5 times? Well, that came out to be our most common value. So instead of actually counting these, I'm going to change this now over to a histogram and hover over the 5, 6 category. Again, pay attention to the brackets there. So we had 19 points. So 19 out of 100. What is the probability of getting a 6 one time? For me, it actually did happen. It happened 1/100th of a time. Some of you might have that happening 0 times. Again, these are likely versus unlikely cases. What is the probability of getting at most 1/6? Well, that would be a 0 or a 1. 0 didn't show up at all. So again, this is still 100.01. Okay. So again, you can see that we have the data centered around 5, which again is expected based on the fact that we have a 1/6 of 30 is 5, right? 6 times 30 is 5. So we're going to kind of take that information to try to analyze some of the questions we have on the next page. If you want to go ahead and read these and try them on your own, I would definitely try to see if you could understand some of them. So if you want to pause the video, go ahead, but I'm actually going to get started. So here we have a simulation of a game spinner. You know, think about like what are some of the games we have that use spinners? Twister, drawing a blank on some of the other ones, but any games that have spinners. So Michelle conducts 100 simulations. So there should be 100 dots on the dot plot, or 100 values, which is why we have 100. If I add up all these numbers, they should add up to 100. It's 100 simulations of 20 spins, which is why my histogram here goes from 0 to 20. The number of times yellow occurs on the histogram. So this is a spinner that's divided into equal sections. And the question that we're actually asking here is, based on the data, how many different colors do you think there are? So how many equal sections do you think there are in this spinner? So to analyze this, we're actually going to look at where's the data centered. And it appears that it's centered around 4. So if 4 was the most common value, 4 is the center of this, 4 out of 20. Think about that. Hopefully that should help you kind of realize this. So if I take 4/20ths, that means that we get a 5th. That reduces to a 5th. So this spinner is most likely, not guaranteed, but most likely divided into 5 equal sections. All right, and yellow was just one of the sections. We could add any of the other colors of the rainbow on there. Okay, so again, if you want to take a chance to read example 4 here, pause your video, but I'm actually going to get started. So 100 simulations of 20 fair coin flips was conducted, and the frequency of heads is shown in the histogram. So again, there's 100 data values. If I add them up, I get 100. Which outcome was most likely? Well, that's the number 10. According to the histogram, how likely is it to get heads at least 15 out of 20 times? Well, 15 is right there, and at least means I'd have to go to there and above. There was only 1 out of, again, I'm not going to bother to add it up because that number tells me it's out of 100, so 0.01. Danny has a coin he flipped, and he flipped 20 times and got 15 heads out of 20 flips. Is it likely that Danny is using a fair coin? So really, this is what we're going into with probability. Is a situation considered likely? To me, if it happened 0.01 times, we would say it's unlikely, and we're going to quantify that better in the next video. All right, but I don't want to go too long here. I've already hit the 15-minute mark. All right.